Distributions are an important concept which we'll be seeing a lot more of from here on out. So suppose you have a random quantity, for example, the result of a die roll, or the delay of a randomly chosen flight. A probability distribution has all of the values of the quantity, all of the possible values. So for example, the result of a die roll, 1 through 6, and the probability of each of these values. So the probability that you see a 1, the probability that you see a 2, and so forth. Or, for example, with a randomly chosen flight, a probability distribution would have all of the possible values of the delay, so 1 minute, 2 minutes, 3 minutes, and so forth, and then the probability of seeing any of these. So here's an example of the probability distribution of a die roll. What we know about a die roll is that each of the results are equally likely. Because of this, we say that the distribution is uniform. So we can put this in sort of a table form here. I have the 6 faces of a die. If I were to visualize the probability of rolling any one of them, what you would get here is this is a histogram showing me the probability of getting a 1 is here. It's 1 over 6, which is between 0.15 and 0.175. The probability of rolling a 2 would be up there as well, at the same exact value. Same for 3, 4, 5, and 6. So this histogram is a way of telling us what's the probability. Remember, if I calculate the area of a bar in a histogram, that tells me the probability of randomly selecting this thing from the data set. So I could calculate this area, and it tells me the probability. A uniform distribution is one which is just flat. The probability is the same for each of the possible outcomes. Think again about the flight delays. So I have a population which consists of all flights from San Francisco International Airport. And then I randomly choose a flight from this population, and I could ask how likely is it that this flight's delay is 10 minutes. So this is a random number, and so there's some probability of seeing a flight delay of exactly 10 minutes. What about 20 minutes? What about 30 minutes? Somehow those seem a little bit less likely. If I go all the way up to like 2 hours, those flight delays do unfortunately happen, but thankfully only rarely, so they're not as likely. So if we were to visualize the distribution here, or how likely it is for each length of delay, we would see a non-uniform distribution, that some delays are more likely than others. And we'll see this actually in just a few slides. So the question is, can I always know what I'll call the true distribution, which is that thing which tells me how likely that each outcome is? It gives me all of the possible outcomes and the probability associated with each. And the answer is sometimes yes, I can, and sometimes no, I can't. So here's an example where I can know about it. So suppose I can reason about what the probability distribution should be. An example of this is rolling a die or flipping a coin. I know that the result of rolling a die is going to be a uniformly distributed random number. It's no more likely to see a 3 than it is to see a 5. So I know the probabilities all have to be the same, so I know that distribution is flat. It is a uniform distribution. Another case where I can know the true distribution is if the population is small. So, for example, if I had my population of 200 movies, and I could ask, what's the distribution of the gross of the movies? Well, I know all of the movies. I can easily calculate those probabilities because I have all of the data available to me. On the other hand, suppose the population is just really, really large and I don't have access to that. Okay, then it's not possible for me to calculate the probabilities. Consider, for instance, the distribution of flight delays. I don't have access to all, however many hundreds of thousands or even millions of flights there have been from San Francisco International Airport. So I can't, in principle, calculate or I can't in practice calculate the distribution of flight delays because I don't have access to that data. So what do we do if I can't do that, if I don't have access to the full population? Well, what we can do is we can draw a sample of flights. So I can go to the airport, I can randomly select maybe 100, maybe 1,000 flights and analyze those and hope that the distribution I see there in the delays is, approximately like the true distribution. It's a subtle idea, but we're going to be seeing more and more of this in the next few lectures. So if I go and I collect a sample and I look at the distribution of the sample, what it is it's called the empirical distribution. So this is a distribution based on observations, perhaps from repetitions of an experiment, like rolling a die over and over and over again. And the empirical distribution contains all of the observed values, okay, and the proportion of the counts of each value, or how many times I saw every outcome. So the idea behind an empirical distribution, why it's useful or interesting, is that it can approximate the true distribution, which is what we're really kind of interested in. Okay, so this is getting kind of theoretical, so let's look at an example. So suppose I wanted to know what the distribution is. What's the probability distribution describing the roll of a die? And of course I know this from theory. I can reason it out that it's a uniform distribution. But another way to do this is to roll a die a bunch of times and find out the distribution empirically with an experiment. So here we go. I'm going to roll a die 10 times. And so how I'm going to do this, remember I have the die table, and it has my population, and it has all of the possible outcomes. I'm going to sample 10 times with replacement. So rolling a die, by the way, is like sampling with replacement. After I get a number, I put it back in, so to speak, and I can select it again on my next die roll. So then I'm going to get let's just run this bit of code here. Okay, so I get a table of results of die rolls. Okay, so I got a 5 on my first roll, then a 4, then a 3, then a 2, then a 4, then a 1, and so forth. What I want to do is I want to see how frequent each result was. How do I calculate probabilities? Is I count how many times did I see a 5, and I divide it by the total number of times I rolled the die. And that's my sort of approximation of the probability. So I'm going to do that by plotting a histogram. Okay, so then I get this. So this tells me that rolling a 1 is much more probable than rolling, for example, a 4, a 5, or a 6. And remember, I can calculate the probabilities exactly by finding the area of this bar. Now the reason that 1 looks a lot more likely than a 5 or a 6 is because I only rolled the die 10 times. If I roll it 100 times, things start to get a little bit more even. If I roll it 1,000 times, things get even more even still. Although 5 here does seem a lot more likely. So then I start really cranking it up. I'm going to roll the die 10,000 times, and things start to look much more even. If I roll this again, or if I run this again, I'm going to get different results, okay, because this is random. Okay, this is the most even result so far, but on any particular run of this experiment, you might see one of the bars higher than the other. This is an empirical distribution. Okay, we know that the true distribution is that perfectly level rectangle. The empirical distribution is my approximation of that I got from running experiments. In this case, there's no real reason to do an empirical distribution, to find an empirical distribution with experimentation, because I know the true distribution. But in a lot of instances, I don't know the true distribution, and I want to know it. The way I get that is with experimentation, as we'll see. So this idea that my empirical sample, my empirical distribution, might look a little strange at first, but then as I kind of crank up the number of samples, it starts to approximate the true distribution, is a major result in probability theory. And so you may have heard of something called the law of averages. And what the law of averages says is just this. If you have a chance experiment that you do a bunch of times, like rolling a die or selecting a random flight, and the selections are independent, meaning that one doesn't influence the other, and you're doing this over and over and over again with the same sampling strategy under the same conditions, then, and here's the important part, the proportion of times that an event occurs kind of converges to the real probability of that event happening. So as I do this more and more times, my estimated probabilities converge to the right probabilities, the true probabilities, if you will. So as I roll a die repeatedly, the proportion of times you see a 5 gets closer and closer and closer and closer and closer to 1 over 6. If I roll that die 10 times, it's not crazy to see the 5 4 times out of 10, which would tell you that the probability is 40%, which it isn't. It's 1 out of 6, which is much lower than 40%. But if I roll that die over and over and over and over again, I'm probably not going to see a 5 40% of the time. If I do, then I think that die might have something strange going on with it. It's not a fair die. So this is like a theorem, or like something you can prove, you can demonstrate in probability theory. The careful statement of this law is a little bit more complicated. You have to understand that sometimes weird things can happen with just very, very small probabilities. But most of the time, you're going to see something. You're going to see the probabilities converge. So if I have a large sample size, like we saw whenever I rolled the die more and more and more, then the empirical distribution kind of matches the true distribution, quote, with high probability, which again sort of means like sometimes you're sampling, you just might get really unlucky and you see a die that's fair, roll 5 just a bunch more times than it should. But in all likelihood, you're going to see the sample be representative of the population. So let's take a look at our flights again. So I have a data set here of United Airlines flights leaving San Francisco International between June 2015 and August 9th, 2015. So here's our data set. It's a big data set. It has 13,000 some rows. For every flight, so every flight is a row in this data set, I have the date, I have the flight number, the destination, and the delay. Notice that some of the delays are negative, which means that the flight actually took off before it was scheduled to. But that's, as we'll see, that's kind of rare. Okay, we only want the delays for now, so let's get just the delays. So now I have a table with one column, which has the delay. Okay, so we're going to imagine that that is the population. Okay, so those are all of the United flights between June 1st and August 9th that left San Francisco International. That's the population. But suppose we don't have the ability to get all of that data. Maybe we don't work for United, we don't have access to that full data set of 13,825 rows. What we're able to do maybe is collect a small random sample. So by going to the airport, randomly selecting flights and seeing how long they're delayed. And we might only be able to sample 100 flights or maybe 1,000 if we have those resources. So let's look first at the distribution of the population. This is what I'd call the true distribution. It's what United sees whenever they look at their data. So what we see here, for example, in this histogram is that the most frequent flight delay is around 0 minutes, or maybe a little bit after 0 minutes. So that's good news. And then what you see here is what you might call a long tail. So this is called a tail, and it goes off towards higher and higher delays. We see that some flights are delayed 100 minutes up to 150, and once you get up to here, the flight's probably going to be canceled. So that's why we don't see too much over here. But the x-axis going all the way to 300 tells us that there was some flight that was delayed for about 5 hours. In fact, let's see what it was. So United get delay dot max. Ooh, 580 minutes. That's a long flight delay. Okay, so let's take a look then at, so this was the population. This is what United sees when they look at all of their data. Now let's take a random sample. This is us going to the airport, randomly selecting maybe 100 flights, okay? And then let's plot what we see. Let's plot our distribution in the flight delays. Think about what you expect to see. So I plot it, and I see something that is kind of similar, okay? But it looks like it's a low resolution approximation of this, right? There's like this bar here, which isn't present in the original data set. That's just due to random chance. That's due to randomly, accidentally selecting flights that had 50-minute delays at a higher rate than it actually occurs in the true distribution, so to speak. So as I crank up the size of my sample, so here going from 100 flights in my sample to 1,000, what I'll see is that my empirical distribution starts to look a lot more like the population distribution. Okay, now if I do this again, if I get my sample again, this is going to look different. Okay, this is like going back to the airport and selecting another 1,000 flights randomly. I get a different 1,000 flights, so the distribution will look different. If I go back to 100, this is going to be clearer. Okay, so there I got 100 flights. I'm going to get a different 100 flights. You see it's different, and so forth. Okay,